we defined last time, this is what we have for now. The definite integral of f of x over the closed interval a comma b, we have defined this to be a to b f of x dx. We know that it gives us area under f of x, the graph of f of x, over the interval a comma b. But at this stage, we have only one way to compute this. We have to do limit n approaching infinity, k equals 1 to n, f of a plus k delta x multiplied by delta x. This is what we have done for now. And we have a criteria. Now we know a function, the type of functions for which the limit on the extreme right will exist. If f of x is continuous, or even if it has finite number of jump discontinuities, we know that the limit on the right-hand side will exist. What we did last time, we started writing some properties of the definite integral, keeping in mind that the integral from a to b of f of x dx gives us the area under the curve over the interval. So I'm going to start with properties again. The first one was if you go from a up to a to b, f of x dx, if you switch your limits of integration, it would be negative b to a f of x dx. If you switch your limits of integration, it gives you a negative sign. And it's basically coming from this delta x that we have in the Riemann sum, the limit of the Riemann sum. Your delta x is b minus a over n. This is how we defined it, b minus a divided by n. Now you can see that if you reverse your a and b, instead you write a minus b, then you get an extra negative sign, which shows up right over here. The second property is if you go from a up to a f of x dx, your lower limit of the integral is the same as the upper limit of the integral. In that case, the definite integral of f of x from a to a would be equal to 0. But once again, we can relate it to our understanding that the definite integral in our notation gives us the area under the curve. We are saying that if this is the function y equals to f of x, we are starting from x equals to a right here. Well, we're not taking any step. We're not moving forward. So we are saying that area under the curve y equals to f of x from x equals to a up to x equals to a, that has to be equal to 0 because we are not moving along the x-axis at all. All right. Next property is just like the one that we had for derivatives and for limits. If you have a to b k f of x dx, k is any constant, you can pull out this constant of the definite integral, k a to b f of x dx. Now, in terms of area, what we are saying is on the left-hand side, it's the area under the graph of k times f of x from a to b. On the right-hand side, we are saying we calculate the area under the graph of f from a to b, and then we multiply it with k. The property says that it doesn't matter which one you do. Either you multiply your function first, or you first calculate the area under f and then multiply your answer with k, you'll get the same answer. Okay, let me just write that down. Area under k f of x over the interval a to b is the same as k multiplied by area under f of x over the interval a to b. Okay, again, I can have a look at it graphically as well. If this is our function f of x defined over x equals to a up to x equals to b, if I multiply it with k, I'm taking k as a positive constant, it will shift all the y values up. This is the graph of k f of x. Everything will be pushed up. Now what we are saying is that if you calculate this area and multiply it with k, is the same as if you calculate this area under the function k times f of x, which makes sense as well. Okay, moving on now. The next one, for a to b f of x plus g of x dx, which would mean area under the graph of f of x plus g of x over the closed interval a comma b. This is what it represents, the left-hand side. This is the same as a to b f of x dx plus a to b g of x dx. Now we are saying area under f of x over a comma b plus area under f of x, g of x, second function is g, over a comma b. So either you add the functions first and then calculate the area under the sum, or you calculate the area under each function separately and add them together. It doesn't make any difference. The same result holds true for difference of two functions as well. So it's plus minus on the left, it's plus minus on the right as well. Okay. The next one, where we can take an intermediate point between a and b. The area under the graph of f of x from a to b is the same as you calculate the area from a to c, and I'll explain what this c is, f of x dx, plus then you start from c and you go up to b, f of x dx, where c is a value between a and b. So you pick any value between a and b, and you can split your area at this value c. Once again, graphically, it'll make more sense. Suppose this is the graph of our function, y equals to f of x, and we are going from x equals to a to x equals to b. This area is exactly the definite integral of f of x dx. What we are saying is that if you pick a point in between, let's say this value c, somewhere between a and b, then you can add up this area and then add it to this area over here. It's the same as the area in blue that we did in the first place. So this would be a to b, a to c, sorry, f of x dx. And this guy here, this is c to b, f of x dx. But c has to be between a and b. Then we can split it like this. All right, now comparison of two functions. Suppose we have two functions f and g. If f of x is always less than or equal to g of x, graphically what we are saying is that the graph of g of x is always on top of the graph of f of x. Then it also implies that the area under the graph of f is always less than or equal to the area under the graph of g of x. The comparison also holds true for interval a to b. F of x is less than or equal to g of x. And once again, once we graph it, it makes complete sense that if this is our function, let's say f of x, and I have my function g of x always on top of it, somewhere here. This is my function y equals to g of x. If we cut everything off from a up to b, you can see that the area under the graph of f is definitely smaller than the area under the graph of the function g of x over the interval a comma b. Well, it'll depend on the comparison. Now, if you are saying that f of x is less than g of x, remember, if you go on the negative side, the number that is more negative is actually a smaller number. And especially because we are talking about the area. So we have to keep things positive. That's why I'm doing everything for non-negative functions, the functions that are above the x-axis. If you go up below the x-axis, then you will have to do the absolute value of the definite integral because the area has to be positive. So suppose my function, this is my function f of x, and or maybe g of x, the way we are writing the comparison. And this is my function f of x, because this is more negative. From a to b, or maybe let's bring it within the interval. Here, this is my x equals to a, this is x equals to b. Now you can involve the absolute value. So you can see that the absolute value of the definite integral of g of x from a to b would be smaller than the absolute value of the area or the definite integral of the area under above the graph of y equals to f of x under the x-axis from a to b. Area wouldn't be negative. I mean, in this case, if I write it in its form without using the absolute value, I can write, so what we have here is g of x is bigger than or equal to f of x, because f of x is more negative. And we can see here now that the area under the graph of f of x, but it's going to have a negative value, dx, would be less than or equal to a to b g of x dx. But just be careful about the negative sign. Area has to be positive, so you have to take the absolute value if you're talking about the area. Okay. Now, another property, and it's very interesting. We say that the minimum value of f over the interval a to b, yeah, absolute value would make it bigger. I haven't put absolute value over here. So in this form, there is no absolute value. But if you put the absolute value, then of course the orange area would be bigger. The shaded region in the orange in this figure would of course have a bigger value. It's just like we are saying in terms of real numbers. -8 is definitely less than -1. But if you take the absolute value on both sides, then we have to reverse the inequality. It has to be 8 bigger than 1. Okay, so now if you take the minimum value of the function f over the interval a to b, and you multiply it with b minus a. And then I take the max value of f over the interval a to b, and I multiply this with b minus a as well. The theorem says that these two serve as the lower bound and the upper bound for the area under the graph of f of x over the interval a to b. We know that the area under the graph of f from a to b is always bounded on the top by max value of f multiplied by b minus a, and below by minimum value of f multiplied by b minus a. Let's see, where is this coming from? Suppose I have my function f of x that looks, let's say, like this. And this is our interval, x equals to a, and this is x equals to b. This is where I cut it off. When I take the integral of f from a to b, I get this all area in green. This whole area is a to b f of x dx. Limits are usually used for example, we had the index k going from 1 to n, the starting value and the ending value. You can say x equals to a is the lower limit for the definite integral, x equals to b is the upper limit for the definite integral. When you know that something is always bigger than something, just like this case, this area is always bigger than this number over here on the left. So we would say that this is the lower bound now. And because this area is also smaller than this one, we would say this guy here, the number on the right hand side, extreme right, is the upper bound. You can also say that for the values of x, because this is x equals to a and this is x equals to b. You can say that x equals to a for the interval is the lower bound, and x equals to b for the interval is the upper bound. So it depends on what if you're talking about. All right, now let's consider the quantity on the left. Minimum value of f over the interval a to b multiplied by b minus a. First, b minus a is the length of the interval. It's this length, b minus a. Exactly this piece, starting from here, and the length of the line from x equals to a up to x equals to b. Now, what is minimum value of f? You can see that the minimum value of f is right here. It comes from the height of this point. Now, if I multiply this height over here with b minus a, I get the area of this rectangle, because the height of the point defines the height of the rectangle, and the width is b minus a. This guy here, this area in red, this equals minimum value of f over a comma b multiplied by b minus a. b minus a is the width, minimum value of f is the height. I get the area of this red rectangle. Now you can see that my green area is always bigger than this red area. So this is the left-hand side of this compound inequality. It's a joint inequality. Now let's look at the maximum value. The maximum value is coming from here. This height, the height of this black line, is the maximum value of the function on this interval, a to b. But then I multiply it with b minus a over here again. If I multiply it with b minus a, it creates the area of this rectangle for me again. The width is b minus a. The height is max value of f. I get the area of all this, the black area of this bigger rectangle. And now you can see that the area of the black rectangle is definitely bigger than the area of the area under the graph of f over the interval a comma b, the area in green, which is the right side of this combined inequality. Okay, it's a very nice result. Let's do some examples on these properties. Suppose we are given that -1 to +1 f of x dx equals 5. The area under the graph of some f from -1 to 1 is given as 5. We are also given as when you integrate from +1 to +4, same function, f of x dx, it leaves us with a negative value. Suppose these two values are given to us. Now I generate more definite integrals. First, what would be the integral from 1 to -1 of f of x dx? So the two integrals on the top are given, and now I'm writing the one that we need to find out. Now, none of my given integrals go from +1 to -1. But I do have a property. I know that if I switch the limits of integral, I get a negative sign. And I know the value of the integral from -1 to 1 of f of x is given as 5. So my answer would be equal to -5. Similarly, if I create another one, what would be the value of integral 1 to 4, 7 f of x dx? Well, I know I can factor out the 7, it's a constant. Let's do that first and write 1 to 4 f of x dx. I know the value of the integral of f of x from 1 to 4. This is given as -2. So this becomes 7 times -2 equals -14. Another one. Now I take, let's say, the integral from -1 to 4 of f of x dx. The integral that I know goes from 1 to 4 and -1 to 1. But because +1 is between -1 and +4, -1 is the lower bound or lower limit, and +4 is the upper limit of the integral, this can be written as, using the properties, -1 to 1 f of x dx, plus I start from 1 and I go up to 4 f of x dx. I break my integral at x equals to 1 because it's an intermediate value. Now I know both the integrals. The first one is given as 5, and the second one is given as -2. In the end, we'll be left with a value of +3. Another example. Show that the integral from 0 to 1 of 1 plus cos x under the root dx is less than or equal to square root of 2. Okay. Now, I will use the right-hand side of the last property that we wrote, which was, we have a to b f of x dx is less than or equal to maximum value of the function f over the interval a comma b multiplied by b minus a. Now, if you compare it with the integral on the left-hand side in black, I can write here a equals 0, b equals 1, and our integrand f of x must be equal to 1 plus cos x under the root. Left-hand side becomes the integral that we have up here. And now we have to show that this is less than or equal to root 2. So I need maximum value of f over the interval 0 to 1. And then I will multiply it with the length of the interval, which goes from 0 to 1. Okay. When you look at f of x, I can say that the maximum value of this function f will come when I will get the maximum value of cos x. For example, if cos x is 0, my answer is 1. But if cos x has a positive value bigger than 0, my value of the function would change as well. But the maximum value that we can get from cosine is plus 1. Cos is always between negative 1 and plus 1. So I can write confidently here that the maximum value of f equals 1 plus cos would be 1 under the root, which is root 2. Now, using our inequality from here, I can write 0 to 1, 1 plus cos x under the root dx would be less than or equal to max of 1 plus cos x under the root over the interval 0 to 1 multiplied by the length of the interval 1 minus 0, which gives us root 2 multiplied by 1, or finally we can write or 0 to 1, 1 plus cos x under the root dx less than or equal to root 2. And that's exactly what we wanted to show. Okay. I'm going to go back to the calculation of the area using the Riemann sums because that's all we know at this stage. So the question now is, example, evaluate the definite integral given by a to b 3x dx. That's what I want to calculate now. But my only choice is the limit of the Riemann sum at this stage. So I'm going to apply that here. So recall that a to b f of x dx by definition is limit n going to infinity, k equals 1 to n, f of a plus k delta x multiplied by delta x. And our delta x, the way we defined it was b minus a divided by n. Now I have to do all this for the function f of x equals to 3x. Let's actually write that down here. Our function f of x equals to 3x, the integrand right here. A equals a, lower limit of the integral. I'm taking general parameters, a and b, or constants. And my delta x with these values would remain as b minus a over n. Now I have to use all this and calculate the limit of the Riemann sum. So let's do that. First, I calculate a plus k delta x. This equals a is a, k is going to be the index, and delta x is b minus a divided by n. Great. If you remember, the next step for us was that we calculate f of a plus k delta x. This would equal f of a plus k b minus a over n times delta x. Delta x is outside. This is my f. I've already used the value of delta x. We'll multiply that with f in a minute. My f is given by 3 times x, and I'm calculating f of a plus k b minus a over n. This would be equal to 3. I go to my function and replace every x by this big chunk over here. It'll be 3 a plus k b minus a divided by n. Great. We have calculated the function. I have done this part. Now I have to multiply it with delta x. F of a plus k delta x times delta x equals 3 a plus k b minus a over n multiplied by b minus a divided by n. Delta x is b minus a over n. Let's do the multiplication here. This equals 3a times b minus a over n. This is an n. Plus 3k b minus a divided by n whole squared. Okay. Now we have all this stuff from here up to delta x. We apply the summation now. This implies summation k equals 1 to n f of a plus k delta x with delta x, that equals summation k equals 1 to n 3a b minus a over n plus 3k b minus a over n whole squared. I apply the summation on every term separately. And remember, the summation is on k. This is 3a b minus a over n. There is no k in it. I am left with the summation of only 1 plus 3 b minus a over n squared summation k equals 1 to n. I do have a k in my second term. Now I apply the formulas. Remember, this is the summation of 1 from n to n. This would be equal to n, this whole summation. And I have the formula for this second summation over here. This equals 3a b minus a all divided by n times n plus 3 b minus a over n squared. And this summation equals n times n plus 1 divided by 2. Rewriting it, n cancels out. And I rewrite this as 3a b minus a plus 3 b minus a squared divided by 2 n times n plus 1 divided by n. I just rearrange the terms a little bit. Now our final task is to apply the limit n going to infinity. Limit n going to infinity k equals 1 to n f of a plus k delta x multiplied by delta x equals, this term does not involve any n, limit doesn't apply on it, plus 3 b minus a squared over 2, limit n going to infinity n times n plus 1 divided by n squared. That should be n squared because that came out of this square on the top. So this should be n squared here. Great. It's n squared plus n divided by n squared, and n is going to infinity. So this whole limit is going to give me leading coefficient from the top divided by leading coefficient from the bottom, which is 1 over 1, and the answer would be 1. So I'm left with 3ab negative 3a squared plus 3 over 2 a squared plus b squared negative 2ab. I expanded the square as well. Further, this is 3ab negative 3a squared plus 3a squared over 2, 3b squared over 2, negative, these two would cross out, and we'll be left with negative 3ab. This crosses out this. And if I combine the terms in A, these two, this gives us, finally, this implies, let's write the whole thing, A to B, 3x dx, which is equal to limit n going to infinity, k equals 1 to n, f of a plus k delta x times delta x, and we have shown that this all equals 3 over 2 b squared minus a squared. Great. Now, because I have this 3 inside, and from the properties of definite integrals, we know that we can factor out this 3 as well. Using this result, I can write here, this suggests this 3 is exactly the same 3 that we get on the right side. But I can make a formula from here that a to b, if I integrate x dx, this would be equal to 1 over 2 b squared minus a squared. Now, for now, just take them as formulas, just for a couple of classes. When we involve the antiderivatives, you would see that it's just very simple. You will see that from here to here, you can go in a couple of steps. It will be very simple. But for now, just take them as formulas. Now, what happened to the a squared terms? So this is what we had. We had 3a squared plus 3 over 2 a squared. If I factor out 3a squared, I have negative 1 plus 1/2, which is negative 1/2. I am left with negative 3a squared over 2. And then I factor out 3 over 2, and I'm left with b squared minus a squared. Okay, so first, I'm writing this formula in black. Another formula, in the same way, you can do the same process and write c, any constant dx, this equals c multiplied with b minus a. Once again, in a couple of classes, it'll be very straightforward. And the last one is a to b x squared dx. This leaves you with 1 over 3 b cubed minus a cubed. I'm going to use these 3 formulas in the next example that I'm about to write after a definition. If you remember, we wrote that the average value of f of x defined over the interval a to b, that was equal to area under f of x over the interval a to b, all divided by the length of the interval, which is b minus a. But now I have a better notation for area under the graph of f of x over the interval a comma b. With our notation, now we can write a to b f of x dx divided by b minus a. Or the way mostly we write it as is 1 over b minus a to b, f of x dx. Okay. So this is how we calculate the average value of the function. Now let me write an example where I want to use these three formulas in black. Example. Find the average value of f of x equals 3x squared plus 2x plus 1 over the interval 1, 2. Okay, I have the formula now, not a problem. We can write average value of f, I'm using a short notation for that, over the interval 1 to 2. That would be equal to 1 over 2 minus 1, b minus a. The definite integral from 1 to 2, 3x squared plus 2x plus 1 dx. The formula that we just wrote over here. The integral gives us the area, and we are dividing it with the length of the interval. Now, first, the factor outside is just 1. And using the properties of the definite integral, I can write 3 can come out, 1 to 2, x squared dx. Then 2 comes out, 1 to 2, x dx. And then last one is the integral of the constant value 1 dx. Now I go back to these formulas in black, where I have the definite integral of x squared, definite integral of x, and the definite integral of the constant term. Using the formulas, 3, this will give me 1 over 3, 2 cubed negative 1 cubed, plus 2. This definite integral will result in 1 over 2, 2 squared minus 1 squared. And lastly, this integral here with constant 1 would equal 1 times 2 minus 1. There's nothing technical about these formulas. There's two-liners in a couple of lectures. This gives me 8 minus 1 plus 4 minus 1, which is 3, 2 minus 1, which is equal to 1. All sums up to plus 11. All right. Now, in the last few minutes, instead of starting the new section, I am going to do another example of definite integral. And the example that I take is oh, you'll have to check the dates on my lab math. I don't remember exactly what the dates are. What about 1 over 2 minus 1? 2 minus 1 would be equal to 1. 1 over 1 would be equal to 1 eventually. Yes, it'll simplify. So let's write the question as evaluate (0 to 1) x 1 minus x dx. And again, just to make a point that at this stage, our only choice is to do the Riemann sums. All right. So here, so for x, you plug in b minus a instead. Jaden, what are you looking at? You mean the evaluation of this integral? No, I'm using the formula. You see, when you're integrating x, you will have 1 over 2, the upper limit square minus the lower limit square. So I did 1 over 2, that's in the formula, my upper limit squared minus my lower limit squared. Yeah, so I'm just using those formulas. Now let's quickly do this. Here, f of x equals x times 1 minus x, and a equals 0, b equals 1, which would make our delta x as 1 minus 0 divided by n, which is 1 over n. Once I have this, I calculate a plus k delta x. A plus k delta x. This would be 0 plus k times 1 over n, which is k over n. Then when I calculate f of a plus k delta x, constructing the Riemann sums, this is f of k over n. F equals x times 1 over x right here, 1 minus x, sorry. This would be k over n. I replace every x by k over n, 1 minus k over n. I'm using this as my function f. Nice. Multiplying them through, I get k over n, negative k squared over n squared. Now I have to multiply this with delta x. F of a plus k delta x times delta x is k over n, k squared over n squared, k over n. This gives us k squared over n squared, negative k cubed divided by n cubed. Okay. All right. Wait. No, my delta x not k over n. Yes, my delta x is not k over n. It's 1 over n. So this is k over n squared and k squared over n cubed. Thank you. Good. Now we apply the summation. K equals 1 to n. F of a plus k delta x times delta x. This equals 1 over n squared, summation of just k, negative 1 over n cubed, summation k equals 1 to n of k squared. Now we recall the formulas. This equals 1 over n squared, n times n plus 1 divided by 2, negative 1 over n cubed, n plus 1, 2n plus 1 divided by 6. That's the summation of k squared. Now we take the limit n going to infinity. So I can write finally 0 to 1, x, 1 minus x dx equals limit n going to infinity of k equals 1 to n, f of a plus k delta x multiplied by delta x. The limit from the right-hand side is 1 over 2 from the first one, negative 2 over 6 from the second term. So 1 over 2, negative 1 over 3, which is 1 divided by 6. Okay. Now you can see that we definitely need some algebraic method that can simplify our calculations for definite integrals. And that's what we are heading towards. The fundamental theorem is going to help us with that.